We've had resistors in circuits before, we've had capacitors in circuits before, but we have yet to have resistors and capacitors together in a circuit. So today, we're going to introduce an RC circuit. We have a capacitor, we have a resistor, we have a battery, and a switch.
And the switch?
Yes, and a switch. Yes. Capacitor, resistor, battery. Initially, the capacitor is going to have no charge on it. Specifically, what we're going to talk about today is charging a capacitor through a resistor. Next time we'll get through the resistor as well, but today we're just going to start with charging the capacitor through the resistor. So, initially uncharged capacitor. Then we're going to flip the switch. And the key to understanding this is to understand that there is a time component now, because the resistor is going to resist the flow of the current, and the capacitor is going to slowly gain charge, which means over time, current is going to change, the charge on the capacitor is going to change, and the potential difference across the capacitor is going to change, all as a function of time. So we're going to start out by using one of Kirchhoff's basic rules, which is that the potential difference across a loop is equal to 0. So we're going to set up the loop. We're going to have this be the direction of our loop. So walk me through it, please. Yeah. This is the direction of our loop.
Positive EMF.
Positive EMF. Then the potential difference across what? The capacitor. So we have to decide whether the potential goes up or down across the capacitor. So as time goes by, we are going to build charge on the capacitor. The bottom plate is going to develop a positive charge, and the top plate is going to develop a negative charge over time. Therefore, Zach, the potential difference across the capacitor is going to be positive or negative? Negative. As we go from positive to negative across the capacitor, the potential is going to go down. Clearly, we are going to set up a current going this direction across the resistor. Therefore, we have the potential difference across the resistor. Zach? Negative. Again, we have a potential difference, and it is going down. So we already have the potential difference across the resistor is current times resistance. We need the potential difference across the capacitor. So by definition, capacitance is equal to Emily? Q over delta V. In other words, the electric potential difference is equal to the charge over the capacitance. Now, big Q we generally identify as the total charge, but we've identified that this charge is changing as a function of time, so instead I'm going to use a little q, and we're going to divide by C. In a few moments, we're going to go through and we're going to derive the equations for the charge and the current both as a function of time. But we're going to start out by understanding the limits. Like, where does this start? Where does it end? So initially, remind me, the charge initial on the capacitor is equal to what, Mr. P? No, it is not equal to Q initially. This is at time t equals 0. So this is time less than 0. This is time greater than or equal to 0. At time t equals 0, Potorella, the charge on the capacitor is? 0. Notice, the initial charge on the capacitor is equal to 0. If the initial charge on the capacitor is equal to 0, we can take this equation. We get 0 equals the EMF minus the current times the resistance. In other words, the current times the resistance equals the EMF, or the current equals the EMF divided by the resistance. And what do we know about this current? This is the initial current, right? At time t is equal to 0. The initial charge is 0, and the initial current, what do we know about it? Jenkins?
It's constant?
It is not going to be constant. It's going to actually change immediately, right after time t equals 0.
Yeah.
What's going to happen to the charge, class? It's going to increase. Therefore, what's going to happen to the current? It's going to decrease. This is our maximum current. At that initial moment, at the very, very beginning, the current is going to be a maximum because the charge is a minimum. If you think about it this way, the potential difference across the battery is going to be equal to the potential difference across the capacitor plus the potential difference across the resistor, right? If we solve this for the EMF. So as the potential difference across the capacitor goes up, the potential difference across the resistor is going to go down, therefore the current's going to go down. Okay, that's at the initial point. What about at time is equal to approximately infinity? What do we know then about the current, for example, through the circuit? Potter up. Why is the current equal to 0? Why is the current equal to 0 if we get to time t equals infinity approximately? John?
Is it going to be because all the, no, I don't know.
That's okay. No?
Because the capacitor's charged, so charge isn't moving anymore?
The capacitor is fully charged. So when the capacitor is fully charged, the potential difference across the battery is going to be the same as the potential difference across the resistor. And therefore, no current is going to be able to flow because this is going to equal this. Therefore, the potential difference across the resistor is equal to 0. So at t equals infinity, Q final equals the total charge, which is whatever maximum charge we have. Now, we can actually figure out what that charge is by using this equation again. Because we get 0 equals the EMF minus Q over C, but current times resistance is gone because the current is 0. Therefore, Q over C is equal to the EMF. The charge final is equal to the EMF times the capacitance, which is the maximum charge. So again, where we started here is with the limits. We know initially the capacitor starts out with 0 charge, therefore the current is at a maximum. We figured out its value, it's the EMF divided by the resistance. We also have, at time t equals infinity, after a really long time, there's no more current flowing because the capacitor is fully charged, and therefore the current final is 0, and the charge final is a maximum. We figured out it's the EMF multiplied by the capacitance. That's the limits. Now we're going to go through and figure out what it is in between those 2 points, 0 and infinity. So we come back to this equation. 0 equals the EMF minus Q over C minus IR. Now, do you understand that this particular thing, which I'm going to go through, is something that you have to be able to derive, and it's something that has come up several times on the AP test. There are several different things that are going to be derived similarly to this, and so when I say that, I'm referring to all of those. This specific one has come up on an AP test, but there are others that are based off of this as well, which you need to know how to do, and this is the first one. Here we go. So let's rearrange. We'll bring current times resistance over to this side. That's equal to the EMF minus the charge divided by the capacitance. Let's just solve for the current. The current is equal to the EMF divided by the resistance minus Q divided by the resistance and the capacitance as well. Just dividing the whole thing by the resistance. On the left-hand side, we know that current is equal to the derivative of charge as a function of time. On the right-hand side, we're just going to get a common denominator of RC. So we have the EMF times R divided by RC minus Q over RC, just getting a common denominator. Now, let's see. We have 1 over RC on the right, so we have dQ over dt is equal to 1 over RC.
Wouldn't that be
EMF C?
Oh, thank you, EC. Thank you. EC, 1 over RC times the EMF times capacitance minus Q. Right, just getting that common denominator. Now, we then need to deal with this dQ over dt. We have Q on this side, so we need to bring Q over to this side. Now, what we're going to do is we're actually going to multiply through by a negative so that we get Q minus EC. You'll see how that works out in the long run here. So please understand that this is probably the step that you probably miss most often. So this particular step, multiplying through by a negative. Now, I'm going to bring the dt over to the other side and the Q minus EC over to the other side. So what we get here is we have 1 over Q minus EC dq is equal to negative 1 over RC times dt. We can now take the integral of both sides. We get the integral of 1 over Q minus EC dq is equal to the integral of negative 1 over RC dt. On the left-hand side, we have the integral of 1 over Q minus EC. Actually, let's start with limits. So what are the limits on charge? Charge varies from what to what? Jenkins?
0 to big Q.
0, actually 0 to little q. Big Q is where it's going to end at time, like time t equals infinity. But remember, our goal is to figure out what it is at any time in between, right? So this is some time between these two limits where charge is just Q, is actually our variable, what we're solving for. What does t vary from then, Catherine?
0 to
It's not going to, again, it's not going to go all the way to a positive Q, just to what? T. Because again, at some time t, we're going to have some charge Q. So these are actually both variables, but both of them start at 0. So now, the left-hand side, we need an integral here. Loki. The integral of 1 over Q minus EC with substitution. We actually don't need to use substitution. He's not seeing it. Help him out. Priscilla?
Yeah, just do the natural log of that, so that Q minus EC. Or that.
It's just the natural log, right? 1 over x. So then from 0 to Q. Let's take the integral on the right-hand side. Integral of the right-hand side. Garrett?
You should do the same thing.
Actually, you need to think it a little bit farther through. It's not exactly the same. Sierra?
Because there's a negative.
No, negative isn't going to affect it. Negative is just a number. Catherine?
negative 1 over RCT.
Do the resistance R and the capacitance change as a function of time? So those are, we can just bring out from underneath the integral. So I'll do it in 2 steps, but we have negative 1 over RC integral from 0 to t dt. So on the right-hand side, it's just t. So we have negative t over RC. On the left-hand side, we have the natural log of Q minus EC minus the natural log of 0 minus EC. Just substituting in our final minus initial. Natural log of 1 minus the other is just 1 over the natural log, bless you, of Q, bless you again, EC over negative EC is equal to negative T over RC. Nissan, how you doing?
I think I'm learning, I'm just not sure what it is.
That's okay. All right, so now, what is our next step? Our goal here is to solve for Q as a function of t. We're trying to solve for the charge as a function of time. Zil,
Raise E to both sides.
we have to take e to the power of both sides. We have e to the natural log of Q minus EC over negative EC is equal to e to the negative t over RC. E to the natural log just cancels out, so we get Q minus EC over negative EC equals e to the negative t over RC. So we'll multiply through by a negative EC here. Q minus EC equals negative EC times e to the negative t over RC. And adding EC to both sides, we get Q is equal to E times C minus E times C times E to the negative T over RC. In other words, the charge as a function of time is equal to the EMF times the capacitance times the quantity 1 minus E to the negative T over RC. That is the charge as a function of time. Now, let's check to make sure that that fits our limits. Remind me, at t equals 0, what was the charge on the capacitor? Hillary?
Yeah.
0. So does this give us 0 at time t equals 0? In other words, class, what's e to the negative 0? 1. What's 1 minus 1?
0.
So it fits for the initial condition. The final condition, the charge was equal to what, Meg? At time t equals infinity.
Big Q.
Big Q, but we also figured out a maximum value for the big Q. Sierra?
EMF times C.
The capacitance times the EMF. So class, what's e to the negative infinity? 0. What's 1 minus 0?
1.
So the charge at time t equals infinity is equal to the EMF times the capacitance. So we figured out the charge as a function of time. We also need the current as a function of time. Nish.
The integral of 1 over q minus EC
Yeah.
is supposed to be out on absolute values, right?
Oh, it doesn't really matter in this particular case, so yeah. Current. Current related to charge. It's just the derivative. The derivative of charge as a function of time. Oh, look, we already have an equation for charge. So we have, so current is going to be equal to the derivative as a function of time of this equation. Let's start with, I think we'll go back here, EC minus EC, e to the negative t over RC. We have to take the derivative of that. Zero.
Aren't E and C both constant?
E and C are both constants. So this, the derivative of a constant is 0. So that whole piece disappears. Good. So we have to take now the derivative of negative, so we'll just do this, I guess. The negative EC, e to the negative t over RC.
Wait, did you already take out EC?
Ah, we did.
No, we're using substitution.
No, just take the derivative.
Oh,
It's free.
I just didn't break down the
I thought you could like take
You
out,
just
like,
multiply through by,
T over RC and there's times 2 with the factors.
so what do we get here then?
Positive
Negative EMF times C times what?
T over R.
We multiply by negative 1 over RC, right? EMF, negative T over RC. So capacitance cancels out, the negative cancels out. We get the EMF over the resistance times e to the negative T over RC.
Can you go to that last part?
Sure. The derivative of e to the power is just, you multiply through by that and remain with the e to the negative.
Why does it have a T? Oh, because it's the derivative.
Right, it's the derivative of this, which is just going to be 1 over RC, or negative 1 over RC. So we end up with the EMF over the resistance. So this is the current as a function of time. Now, notice that that would be the current maximum multiplied by e to the negative t over RC.
This derived, yeah, derived that.
Oh, yeah.
Wait, so that has to be memorized?
So, no, you need to know how to do this derivation.
Alright, so starting with the 0 equals.
Starting all the way back with what was erased here.
Okay.
Okay. Now, let's again check our limits. Current initial was, what did we know about current initial?
It was E over R.
And it was a maximum, right? So at time t equals 0, e to the negative 0 class? 1. So we get the EMF over the resistance. Okay. At time t equals infinity, what do we know about the current? 0. Therefore, e to the negative infinity is 0. We get 0. We should also identify what these look like in terms of graphs. So the charge as a function of time and the current as a function of time. The charge as a function of time. Please give me what the graph is going to look like. Again, Emily, where did the charge start?
At 0.
At 0. Where does it end, Emily?
At positive Q.
At positive Q, which was equal to the capacitance times the EMF, right? And what happens between those two? What does the shape of this graph look like? It's going to go up, look like this, and it's going to asymptote at the EMF times the capacitance. What about the current? Remind me again, Mr. P, where did the current start? The current did not start at 0. Where did the current start? No, wait.
Next.
It started at the current maximum, which had a value of the EMF divided by the resistance. Where did it end, Zach? At 0. And in between, it looks like this, if you follow our equation.